2x minus y plus 0z. So z actually can be anything. Again, it's going to be another plane. Each row in a 3 by 3 problem gives us a plane in 3 dimensions. So this one is going to be some other plane. Maybe I'll try to draw it like this. And those two planes meet in a line. So if I have two equations, just the first two equations in 3 dimensions, those give me a line, the line where those two planes meet. And now the third guy is a third plane, and it goes somewhere. Okay, those 3 things meet in a point. Now, I don't know where that point is, frankly, but linear algebra will find it. The main point is that the 3 planes, because they're not parallel, they're not special, they do meet in one point, and that's the solution. But maybe you can see that this row picture is getting a little hard to see. The row picture was a cinch when we looked at two lines meeting. When we look at 3 planes meeting, it's not so clear, and in 4 dimensions, probably a little less clear. So, can I quit on the row picture? I'll quit on the row picture before I've successfully found the point where the 3 planes meet. All I really want to see is that the row picture consists of 3 planes, and if everything works right, 3 planes meet in one point, and that's the solution. Now, you can tell I prefer the column picture. Okay, so let me take the column picture. That's x times, so there were 2 x's in the first equation, minus 1 x's, and no x's in the third. It's just the first column of that. And how many y's are there? There's minus 1 in the first equation, 2 in the second, and maybe minus 3 in the third. Just the second column of my matrix. And z times no z's, minus 1 z's, and 4 z's. And it's those 3 columns, right, that I have to combine to produce the right-hand side, which is 0, minus 1, 4. Okay. So what have we got on this left-hand side? A linear combination. It's a linear combination now of 3 vectors, and they happen to be, each one is a 3-dimensional vector. So we want to know what combination of those 3 vectors produces that one. Shall I try to draw the column picture then? So since these vectors have 3 components, so it's some multiple. Let me draw in the first column as before. So x is 2 and y is minus 1. Maybe there's the first column. Y, the second column has maybe a minus 1 and a 2 in the y's and minus 3's, somewhere there possibly, column 2. And the third column has no 0, minus 1, 4. So how shall I draw that? So nothing in this was the first component. The second component was a minus 1, maybe up here. That's column 3. That's the column 0, minus 1, and 4. This guy. So again, what's my problem? What this equation is asking me to do is to combine these 3 vectors with the right combination to produce this one. Well, you can see what the right combination is, because in this special problem, specially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work? I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1. That's the combination. None of that. One of those is obviously the right one. So this column 3 is actually the same as B in this particular problem. I made it work that way just so we would get an answer, 0, 0, 1. So somehow that's the point where those three planes met, and I couldn't see it before. Of course, I won't always be able to see it from the column picture either. It's the next lecture, actually, which is about elimination, which is the systematic way that everybody, every bit of software too, production large-scale software would solve the equations. So the lecture that's coming up, if I was to add that to the syllabus, will be about how to find x, y, z in all cases. Can I just think again, though, about the big picture? By the big picture, I mean, let's keep this same matrix on the left, but imagine that we have a different right-hand side. Oh, let me take a different right-hand side. So I'll change that right-hand side to something that actually is also pretty special. Let me change it to, suppose if I add those first two columns, that would give me a 1 and a 1 and a minus 3. There's a very special right-hand side. I just cooked it up by adding this one to this one. Now, what's the solution with this new right-hand side? The solution with this new right-hand side is clear. Now I took one of these, and none of those. So actually it just changed around to this when I took this new right-hand side. Okay. So in the row picture, I have three different planes, three new planes meeting now at this point. In the column picture, I have the same three columns, but now I'm combining them to produce this guy. And it turned out that column 1 plus column 2, which would be somewhere there is the right column. One of this and one of this would give me the new B. Okay, so that's like we squeezed in an extra example. But now think about all B's, all right-hand sides. Can I solve these equations for every right-hand side? Can I ask that question? So that's the algebra question. Can I solve AX equal B for every B? Let me write that down. Can I solve AX equal B for every right-hand side B? I mean, is there a solution? And then, if there is, elimination will give me a way to find it. I really wanted to ask, is there a solution for every right-hand side? So now, can I put that in different words? In this linear combination words? So in linear combination words, do the linear combinations of the columns fill three-dimensional space? Every B means all the B's in three-dimensional space. So do you see that I'm just asking the same question in different words? Solving AX, oh, that's very important. A times X, when I multiply a matrix by a vector, I get a combination of the columns. I'll write that down in a moment. So that, you see, but in my column picture, that's really what I'm doing. I'm taking linear combinations of these three columns, and I'm trying to find B. And actually, the answer for this matrix will be yes. For this matrix, for this